Hello and welcome. I'm Stefan Schneider from Paderborn University, and I'm going to present our paper on self-driving network and service coordination using deep reinforcement learning. So as you can see, this is joint work together with colleagues from Paderborn University and from Huawei. So let's get started. Let's have a look at the scenario and the motivation of this work. In network function virtualization, but also when we talk about microservices in a service mesh, or even machine learning functions in a pipeline, we often have services that consist of multiple chain components. I just called them C1, C2, but could be C3, C4, C5, and so on. And these components could be things like firewalls, web servers, video optimizers, or machine learning functions that do some kind of data processing. Now, in addition to that, we have our network consisting of distributed nodes, each node with some kind of limited compute capacity. And then we have traffic that arrives at the node's ingress nodes. Here, we assume that traffic are really rapidly incoming requests, rapidly incoming flows from our many different users that want to use our service. In order to provide that service to our users, we need to scale it. We need to place instances of all our different components at nodes in the network. And we need to schedule all these rapidly incoming flows to these instances at runtime. So for example, we could place an instance of component C1 at the ingress node directly, and maybe an instance of C2 at the neighboring node. And when we do such placement, we have to, of course, respect the node's compute capacities. And here we assume that these instances do not require, do not require fixed resources, but that the resources per instance are relative to the load that each instance is currently processing. So that means that we can directly control that, or it's directly affected by how we balance the load among different instances and how we schedule incoming traffic to these instances. To illustrate, for example, I could send incoming flows just through this one instance up here and then to my component of C2 down here. And if I would notice that my load is too high here and the resource consumption is too high at the ingress node, then what I could do is I could scale out. I could place a second instance of C1 also at this neighboring node, and then send some traffic through that instance down here. And by doing that, I could balance the load and the required resources among these two nodes. Of course, in this scenario, nothing is static. Everything keeps changing. And in particular, the rapidly incoming user flows keep changing. And we could also have new users at new ingress nodes. And of course, we need to adapt to that and quickly react, changing our scaling, our placement, and also our scheduling online. Now, this whole network and service coordination problem is not new, so there is a lot of existing work. But when we looked at existing work, we found at least three major assumptions, three major limitations when trying to apply this existing work to practice, and that's what we're addressing in this work here. So let's have a look at what these limitations are. So first of all, most existing work focuses on mid to long-term planning per deployment request. So they assume a slightly different problem scenario here, where they say, okay, we get deployment requests maybe from the service provider every now and then, maybe one or two every now and then we have time to run our algorithms, decide which instances to place where, how to hardwire the ingress nodes with these instances, and do all that based on some kind of estimate for the user demand in the next time interval. And then we run all of this and hope that it works. The problem with that is that operation reality often diverges from any such initial plan, and the actual load that we see might be different than what we expected, and then things easily break. So what we do here is we really look at these rapidly arriving user flows that arrive at runtime that want to use the service, and we schedule these flows at runtime, and at runtime or online change our scaling and placement. So our scenario here is a lot more fast-paced, a lot more dynamic. Then the second limitation of existing work is that typically still conventional approaches like mixed integer linear programs or heuristics are used that are designed by experts and tailored to some kind of specific scenario or scenarios. And for those scenarios, they work very well. But the problem is that they're built on some kind of rigid models and quite rigid assumptions that easily break if the scenario changes a bit. So for example, if we try to apply them in practice and the traffic pattern is different, for example, we suddenly have stochastic flow arrival, then if they're not built for that specifically, then easily they completely break or at least work a lot worse. And then again, we need an expert to sit down, understand, and fix them. So what we instead want is a self-adaptive approach that adapts itself to new scenarios, to new traffic patterns, but also to new objectives without any need for human intervention and or expert knowledge. And then lastly, a big limitation of a lot of existing work is the assumption of global, sometimes even up to a priori knowledge of the complete network state. And that's, of course, not realistic in large-scale practical scenarios. Of course, we can monitor what is going on to get an overview of what's happening in the network, but this information will not be completely up to date for fast-changing things like compute utilization, node utilization, or traffic. There will always be some kind of monitoring delay. For example, in Prometheus, it's 1 minute intervals by default. And certainly we will not know the traffic a priori for the next time step. And so in this work, we really work with realistically available information or realistically available partial and delayed observations as they could be available in a monitoring system. And so what we propose is self-learning coordination with model-free deep reinforcement learning. So I know those are a lot of buzzwords, so let's have a look at how this really works. So one core part of our idea is what we call scheduling tables that we deploy at each of our compute nodes. And those scheduling tables basically hold rules that are applied to each incoming flow at runtime locally, and that describe what should happen to these flows. In addition to that, we have a centralized reinforcement learning agent that observes the network through monitoring, so that gets partial and delayed observations from the network about the node utilization, about the traffic through monitoring, and then could see, for example, that load is increasing here, that the resources at this ingress node become highly utilized, and then it could update these scheduling rules that we have in these tables to, for example, send a larger portion of traffic to the neighboring node here, and by doing that, avoid oversubscribing the resources here. This cycle of monitoring and updating the rules repeats iteratively, for example, whenever new monitoring data is available. And during training, we give the agent always a reward that indicates whether we're happy with the solution that it found or whether not. And then based on this, the agent learns how to achieve the desired objectives. Let's have a closer look at how these scheduling tables work. So as I mentioned, we have these scheduling tables at each of our compute nodes. And what they contain is basically information where to schedule each incoming flow based on the service that it requests and based on the component within the service that it requests. So for example, if a flow arrives here at our ingress node v1, and then we'll look at the scheduling table of v1. Let's just say the flow requests service s1, and inside the service it requests the first component c1. Then we'll look at the scheduling table, and we see that with 10% probability, we schedule the flow to be processed locally at v1. With 40%, we schedule it to the neighboring node v2 and process it there. And with 50% probability, we schedule it to node v3 and then process it there. Let's assume by chance that the flow arrives and is scheduled to be processed locally at v1. So it completes processing at component c1 and then directly requests the next component in the service, which is c2 in this case. And again, we look at the scheduling table or at the entry in the scheduling table that corresponds to service 1, component C2, and we see that in this case, the flow is sent and scheduled to be processed at node V5 with 100% probability. So we schedule the flow to go to V5 and be processed there. Yeah, when we're sending the flow there, we take the shortest path from the current node, so we do not optimize routing explicitly here. And the challenge is now to optimize these probabilities, or how the flows are balanced between the nodes, so these scheduling tables, in a way that avoids overloading the compute resources at the different nodes, that avoids sending flows to nodes without the requested components, without the instances, and at the same time also to keep the end-to-end delay short. What we do is, rather than deciding the scaling, placement, and scheduling all separately, first doing the scaling, then deciding where to place these instances in the network, and then deciding how to schedule flows to these placed instances and only to these placed instances, we do all three things jointly together in a single step. We do that by deriving the scaling and placement from our scheduling tables. So what we do is we decide the scheduling tables, and then we look at them and derive where to how to scale and where to place instances of our components based on where flows could possibly arrive. So we start at the scheduling tables of our ingress nodes here, and we look at where flows could arrive. So for example, here for C1, we can see that flows may arrive at node V1, at node V2, and at node V3, but at least based on this table, they may not arrive at V4 and V5, and so we can place instances of C1 here at V1, V2, and V3, but we don't necessarily need them at V4 and V5. Yeah, so now we know how to do our scaling, placement, and scheduling when we have these scheduling tables. So to get these scheduling tables, we need to formalize this problem as a Markov decision process, because we only have partial observations, not the complete network state. It's a partially observable Markov decision process. In particular, our observations contain the average incoming data rate per ingress node within the last monitoring interval, and then also the maximum resource utilization per node also in the last monitoring interval. Based on these partial and delayed observations, the agent takes actions, and the actions specify these scheduling probabilities per node, per service, per component. So basically all these entries that you saw earlier in the scheduling table that decide where flows should be sent. There's an additional constraint here that says that each row of the scheduling table needs to sum up to 1. So we need a probability distribution for each row over all possible target nodes. And so overall, this constraint, but mostly the fact that we have this large continuous action space, because these probabilities can be anything between 0 and 100, is one of the reasons that makes this problem so challenging. And then finally, we also define the reward as a generic utility function that could be any weighted sum of, or any sum of weighted objectives. In our case, we decided to optimize two objectives. First, the fraction of successful versus drop flows. So we want a lot of successful flows and as few as possible drop flows. And then finally, also the negative end-to-end delay. So we maximize the negative end-to-end delay, meaning we minimize the end-to-end delay to get good service quality. And what's important here is to normalize these two objectives to the same range. We normalize them to -1 and 1, so that they're in the same range and more comparable, in a not one objective always outweighs the other one. Yeah, so now we need to solve this partially observable MDP, and for that we propose a deep reinforcement learning framework that builds on deep deterministic policy gradient, DDPG, which can handle such large and continuous action spaces as we have in our problem here. Previous algorithms like DQN cannot do that. And so DDPG is an actor critic algorithm. So it has neural networks for both the actor and the critic. The critic looks like this. So it gets an observation and an action, and it estimates the long-term value Q for taking the action after observation O. And that's then used to train the actor. And the actor is what really decides which action to take. So it gets an observation. For us, it consists of the ingress data rate and the node utilization, and it outputs an action that specifies these scheduling tables. And because we have this constraint that each row in the scheduling table should be a probability distribution, so summing up to 1, we apply different softmax, or we apply the softmax activation function separately to the different parts of the output to get these probability distributions. Now, using this, our framework looks like shown in this figure. So on the left side, we have the network, which is monitored periodically, and the monitoring data is processed by an adapter here that retrieves the relevant information and produces the vectorized observations for the agent, and also computes the reward. Based on this, the actor returns an action to take that's also processed by the adapter that gets the scheduling probabilities, prepares these scheduling tables, and also drives the scaling and placement as discussed earlier, and applies it to the network. Now, this cycle repeats, as I mentioned earlier, and during training, we repeat it a lot of times, so it's time consuming, but we do it upfront offline. And during training, we want to encourage exploration. So we want that the agent explores different actions and explores different scheduling and scaling and placement probabilities to find a good one. And to encourage that exploration, we add random noise to these actions. And then during inference, after training, after our agent converged, it can inference, it can do the scaling, placement, scheduling very quickly and online, because we do not need to train it anymore. We do not need to do any backpropagation of these neural networks anymore. And in that case, we also want to exploit the best actions that we have, so we do not add any more noise. So let's have a look at how our approach performs. Let's have a look at our evaluation. We evaluated our approach on 4 real-world network topologies, looking at a service of 3 components and at traffic following varying, mostly stochastic traffic patterns, but also real-world traffic traces. We compared our approach against 3 algorithms. First of all, a state-of-the-art heuristic called BSP from our previous work, where we had the code available, and also against 2 simpler baselines, the shortest path-based baseline, so that tries to place everything as close as possible to the ingress node to minimize end-to-end delay, and then one baseline that balances the load equally among all nodes to minimize the amount of dropped flows. So first, let's have a look at maximizing the successful flow. So first, just maximizing the first objective and not at all trying to minimize the end-to-end delay. For that, we look at the Abilene topology. So this is a US network. And we look at that with increasing nodes. So particularly, we first look at that with 1 ingress node, and 2 ingress node, 3, 4, 5. And at each ingress node, flows arrive at the same traffic pattern and the capacities are fixed. So the load in the network increases with more ingress nodes. For the traffic arrival at these ingress nodes, we considered different flow arrival patterns. So we started with the simplest case, just fixed deterministic flow arrival, flows arriving every 10 time steps fixed. Then we made it a bit more realistic, but also complex, looking at Poisson arrival with a fixed mean. And then again, made it a bit more complex, but also realistic, looking at Markov modulated Poisson process with 2 Markov states switching between high and low traffic arrival. And then lastly, we looked at real-world traffic traces that we found for this Abilene network. I'm just showing the results for the last case here, but all the plots are in the paper and they're all quite comparable. So what you can see here is on the horizontal axis, the number of ingress nodes, so indicating increasing load. And on the vertical axis, the % of successful flows. And what you can see is, first of all, our approach, the DRL approach, is much better than all of the other approaches. So that's the most important thing. What you'll also notice is that the BSP heuristic, state-of-the-art heuristic, performs surprisingly bad, right? So of course we looked into this, And the issue here is exactly what I mentioned at the beginning. So when designing this BSP heuristic a few years ago, we did not have this stochastic traffic arrival in mind, where flows partially overlap, and yeah, all these rapidly arriving flows are there. And with this changed scenario, it just didn't perform very well, and things were breaking. And so we had to sit down, analyze the problem, and we made an improved version that we call BSP Advanced. And this version performs much better than the simple baselines, but still significantly worse than our deep reinforcement learning approach. So to summarize, our approach self-adapts successfully to varying traffic load, so varying number of ingress nodes, varying traffic patterns. And it does that successfully, processing more flows than all of our compared algorithms. We also checked and saw that our algorithm, or our deep reinforcement learning approach, generalizes to unseen traffic patterns. So we trained it on Poisson traffic, and then without retraining it, applied it to MMP and to fixed traffic, and it still worked, slightly decreased performance, but still better than all of the other approaches, which is great because in practice, traffic patterns may change and our approach should still work while we, for example, retrain a new version that's specialized in a new traffic pattern. Now let's have a look at varying the objectives. So not just looking at maximizing the throughput, maximizing the successful flows, but also minimizing the end-to-end delay. We can tune this by tuning the objective weights indicated here by alpha. And if we fully set alpha to 0, we fully optimize for low delay and not at all for throughput. And we can see that in this case, the agent does learn to fully optimize this delay utility here, of course, at the cost of decreased throughput. So these are conflicting objectives. And then as we tune this objective weight, it starts to process more flow successfully. So the flow utility here increases, but the delay utility decreases a bit. When we compare this total utility with all of the other approaches, we can still see that for each or any of these settings, our approach still outperforms the compared algorithms. So this is really nice because we can see that our approach adjusts to different objectives just by changing the objective weight and retraining, but without any need for expert knowledge. So now lastly, let's have a look at scalability of our approach. So we looked at networks of increasing size, as I said, the US network, a European network, China Telecom, and then a global network with up to 53 nodes and 90 links. We first looked at training. So what you can see here is the training reward over episodes. And you can see that within the first 100 or 200 episodes, the agent quickly improves the reward and quickly learns a very good policy. And what you also can see is that for especially large networks here, the 42 network, that longer training still leads to some jumps in performance sometimes. So this is quite known in deep learning that excessive training can still boost performance, but we had to stop at some point here. So we did not see such jumps here for the 53 node network, even though we expect those might happen later on. So looking at the quality when applying these trained agents, we can see that even here with increasing network nodes, our approach can still compete with or even outperform all of the existing or all of the compared other approaches. So it's still similarly good or better, especially here in the 42 node case where we saw this jump performance during training. And what's also very nice is when we look at the inference runtime, we can see that the runtime of our approach, this is a log scale, is quite stable here with increasing network size, and it's well in the order, it's well below a second, so it's in the order of a few milliseconds here. So let's conclude the talk. So we proposed a self-learning deep reinforcement learning approach, and we saw that this works very well with realistically available information, so partial and delayed observations. It outperforms state-of-the-art approaches, for example, this heuristic. It self-adapts to new scenarios, to new objectives without any human intervention, without any expert knowledge, and it scales to large practical networks. So we believe that this is an important step towards truly driverless networks in practice, which means higher efficiency, higher flexibility, and higher reliability. So Thanks a lot for your attention. If you're interested, feel free to check out our open source repository, so all the code is there publicly available. Thank you.